In Precalculus Lesson 10, we will be looking at complex zeros of polynomials, starting with a review of complex numbers. This lesson comes from section 2.5 in the college algebra textbook. Let's get started by looking at x squared plus 1 equals 0. For this equation to have a solution, it would have to be true that x squared equals negative 1. So up to this point, we've said, well, there's no solution here, but there's actually no real solution. We do have a solution. The solution would be x equals plus or minus the square root of negative 1. And here we're going to define the square root of negative 1 to be the imaginary unit I. So in other words, I squared equals negative 1, and if c is a real number with c greater than or equal to 0, then the square root of negative c is going to equal the square root of c times I. We can take a look here at the square root of negative 4, where our c would be 4 here, and we can rewrite the square root of negative 4 as the square root of 4 times I, and simplify then to get 2i. Let's take a look at multiplying square root of negative 2 times square root of negative 5. Note that both of these are non-real numbers, and I'm going to begin by rewriting square root of negative 2 as square root of 2i, and I'm going to rewrite square root of negative 5 as square root of 5i. Okay, now we can multiply square root of 2 times square root of 5 to give us square root of 10. We have square root of 10 times I squared, keeping in mind that I squared is equal to negative 1. We can write our simplified version here as negative square root 10. What about square root of negative 2 times negative 5? Since both of these numbers are under the square root sign, we can go ahead and work with these to give us square root of 10. So we can multiply these two negative numbers together as long as they're both underneath the square root sign. Let's define a complex number as a plus bi, where a and b are real numbers, and here a would be the real part of the complex number and b would be the imaginary part of the complex number. Okay, so some examples of complex numbers. 3 plus 7i. Here we have our real part of the number here, we can see, is 3. So this would be our a here. Our b would be the imaginary part of this complex number, or 7. So how about the number negative 3? That looks like a real number. Well, real numbers are considered complex numbers as well. Think of this as being negative 3 plus 0i. We would have a equals negative 3 and b equals 0 here. Negative I, well, this looks like a totally imaginary number, but in fact, if we think of this as 0 minus I, or 0 plus a negative I, we can identify a as being equal to 0 here, and b as being equal to negative 1. Now, moving on to adding two complex numbers together, 2 plus 3i plus 4 minus 5i. We simply add the two real parts of these numbers together, and we add the two imaginary parts of these numbers together. So we have 6 minus 2i as our result. Let's multiply 2 plus 3i times 4 minus 5i. The same complex numbers we had before, but here we're multiplying. So we can think of foiling here. We have 2 times 4 is 8. And then we would have minus 10i plus 12i minus 15i squared. Simplifying, we get 8 plus 2i minus 15 times, remember, I squared is negative 1. And simplifying further, we have 2i plus 15 plus 8 would give us 2i plus 23. All right. I actually wrote that backward. We like to put the real number first, so I should actually write that as 23 plus 2i. Okay, sorry about that, but at least I remembered to fix that. So let's go on then. 2. Multiply 2 plus 3i times 2 minus 3i. So again, we can think of foiling here. We have 4 minus 6i plus 6i minus 9i squared. Notice that negative 6i plus 6i, these add to 0. And we are left with 4 minus 9 times negative 1, or 4 plus 9, 13. So what's interesting here is that I'm multiplying two non-real numbers together and I'm getting a real number. Well, the reason that we can do that here, and something that we'll spend a lot more time with, is that 2 plus 3i and 2 minus 3i are complex conjugates. In general, we think of having a number a plus bi. The complex conjugate of that number would be a minus bi. All right, well, let's identify the complex conjugate of a couple numbers here. 6 minus I. So this is the complex conjugate here. We would simply change that negative to a positive here, and we would have 6 plus I. What about I? Think of this as being 0 plus I. Then the complex conjugate would be 0 minus I, or simply negative I. What about 3? Well, 3 is not a complex number, so it does not have a complex conjugate. Keep in mind that only non-real numbers are going to have complex conjugates. Let's divide or simplify this fraction 2 plus 3i over 4 minus 5i, starting by identifying the complex conjugate of the denominator. We have 4 minus 5i. The complex conjugate would be 4 plus 5i. And then we're going to multiply this fraction by 4 plus 5i over 4 plus 5i. This is similar to rationalizing the denominator that you've done before. So as we move on, we have 2 plus 3i times 4 plus 5i in the numerator. And foiling those two together, we would get 8 plus 10i plus 12i plus 15i squared. In the denominator, we have 4 minus 5i times 4 plus 5i, or 16 plus 20i minus 20i minus 25i squared. Again, we see that we have 20i minus 20i gives us 0, add to 0, and we can simplify further to get in the numerator 8 plus 22i plus 15 times negative 1. In the denominator, then we would have 16 minus 25, and then remember I squared is negative 1. We're almost there, so 8 minus 15 would give us negative 7, and then plus 22i in the numerator over 41 in the denominator. So this would be our final simplified answer, and our goal here was to get a real number in the denominator. We've done that. Now we're going to multiply x minus 2 plus 3i times x minus 2 minus 3i. And I've printed some help out here for us. So we can write this as distributing this negative through. We'd have x minus 2 minus 3i times x minus 2 plus 3i. And then we'll take our x here, distribute our x through to x to negative 2 to 3i. We have x squared minus 2x plus 3ix. We move on to distributing negative 2 through to give us minus 2x plus 4 minus 6i, and then distribute through with negative 3i, where we would have minus 3ix plus 6i minus 9i squared. Well, if we look here, there's some terms here that add to 0. Negative 6i plus 6i adds to 0. 3ix minus 3ix adds to 0. And moving on from there, we can see that we have x squared minus 4x plus 4 minus 9 times negative 1. We're almost done. X squared minus 4x, and then 4 minus 9 times a negative 1 is 4 plus 9, or 13. So we have a final simplified answer here of x squared minus 4x plus 13. Now try on your own. Use a complex conjugate to simplify the following: 5 minus 7i over negative 2 plus 3i.